Section 4.3 is about graphing things on your calculator, and not everything fits neatly into this viewing rectangle that you have on your calculator. As you know, we've had to adjust window, and we have to kind of manipulate it so that we can actually see the function. It doesn't necessarily, in fact, most functions don't exist in this beautiful 10 by, actually a 20 by 20 viewing rectangle, because it goes from -10 to +10 and whatnot. What we're going to do next is figure out, are we looking at the entire function? Because we might look at a function, it might look like this, and we think, oh, we've got everything. And it we make the rectangle even bigger and make it even bigger. But let's just say way out here does this whoop-de-doo thing. And let's say you make the rectangle even bigger. You go, I think it's not going to change. It's not going to change. Yep, I keep making it bigger, and look, it just kept doing that. So it's my belief that the function always continues on going up. And even way out here might do a little something. So you've got to be able to figure out, where does it change? Where does it change from, say, increasing to decreasing? Oh, wait, first derivative test, that'll get me that. Where does it change from concave up to concave down? Those are points that we need to look for. First up, they ask you to identify the domain. That just means figure out where it fails to exist, or where it does something weird. So we're looking for where it fails to exist, or like in a square root function. A square root function typically looks like this. So it doesn't have anything over in here, but it might be shifted to the left or right, and you need to know exactly where that is. Or you might be looking at, say, a log function that looks like this, and you need to say, oh, I don't really need anything over on this side, so I don't really need to graph this part. So know where the important differences, or where the important part of the landscape would be on your graph. Symmetry, if it's an even symmetry, and well, if it does this on one side, it's going to do it on the other side. Finding the first and second derivatives, let me know where it's increasing and decreasing and going concave up, concave down, so that we can find these critical points and inflection points. And then we're going to find these extreme values, and we know that they occur at these critical points. And then the inflection points tell us where it changes the shape of either something like this or something like this on the curve. And then, of course, knowing what my horizontal asymptotes are, so I can list that on the graph and note it as significant. Finding the x and y intercepts is also very important, and we want that appropriate graphing window, and we get that appropriate graphing window by making sure we have all these significant points that's going on this graph. Make sure that we have that in our viewing window. So we're going to look at some functions, these examples next, and the questions in your section 4.3 are meant to have weirdo things that happen in your calculator. They know what it looks like in your calculator, and they want you to figure out what's the best viewing window. So we're going to look at that. First up, we're just supposed to give a possible sketch. They've given us the significant points, 0, 1, 2, 3, and 4. So let's make some sort of line, and I'll get a quick sketch, and then I'll draw something a little better. And we're going to say what's going on in each one of these sections as well. So from -infinity to 0, the fact that the first derivative is less than 0 tells me that it's decreasing. The fact that the second derivative is greater than 0 tells me that it's decreasing, and it's doing this concave up kind of shape. From 0 to 1, I know that it is now increasing because the first derivative is greater than 0, and it is still concave up. Okay? So I got to 1. From 1 to 2, it's still increasing. Oops, I'm going to go through my words here. And it has now changed to concave down. So from 1 to 2, still increasing, but it's changed to concave down. Okay, I hope I don't have to go up any higher. Nope, I get to go down. Good. And so it's decreasing and it is concave down. So I'm going to make sure I go down pretty good amount here. So I have room to go up again. So that's still concave down. What happens from 3 to 4? Still decreasing, but now it's concave up. Then I get to 4, and 4 it's now increasing and concave up. So that's going to look like this. And as long as you have the increasing decreasing thing, it could have gone like this, could have up to here, then it goes, oh, at 1 it's still going up, but it does this, then it changes to concave down. Let's just go down just a little bit, and then oops, yeah, see, that's way better. Not really. Anyway, I've messed up my little points, but I'll do it like this. There's my 0 point. My 1 point is where it changes from concave up to concave down, so right in there has to be my 1. My 2 happens to be at that maximum point. And my 3 is where it changes from concave up to concave down, and my 4 is that bottom point. Okay, there we go. Another stunning graph. And you could draw it an infinite number of different ways. Example 2, we have a function I graphed in a standard window. The next one, and this is just a standard -10 by 10, you can see I can't tell any, that definitely isn't the graph. Then I asked it to zoom out, and I asked the calculator to use its massive intelligence to zoom out, and that's the picture I got. I really don't think that's it either. So let's follow our guidelines for graphing. Step number 1, I look at the domain. I try to see if there's any restrictions. Doesn't look like it to me. I don't see anything. So the domain for this is going to be from -infinity to +infinity. Nothing I really need to rule out in that. Next, I need to look at the symmetry. This one is an odd function. It has odd power, so I'm going to look for this function to have that odd symmetry, or that origin, or that flip-flop kind of thing that we talked about in chapter 1. Find the first and second derivatives. Alright, f prime, this is so that we can do the increasing, decreasing, and concave stuff. For f prime is going to be, looks like just plain old, if I bring that 3 down, cancels with that one, so it's just plain old x squared minus 400. F double prime is then going to be 2x. Okay, so I found those. I need to find possible critical points and points of inflection, so set each one of these equal to 0 and see if I have any places where it fails to exist. This thing factors into x plus, that would be 20, x minus 20. Therefore I know that x equal plus minus 20 are critical points. F double prime 0 equals 2x. X equals 0 is a possible point of inflection. Okay. How do I tell? Well, draw this number line here. I'll put a -20 here, and I'll put a 20 here. I need to see if the first derivative is positive or negative here, so I'll just plug in some numbers, say -30. This would be a negative, that would be a negative, so negative times negative is a positive. That means this function is increasing. at this particular point. And here, let's look at f prime at 0, and I would get a positive and a negative, meaning this thing would be less than 0, so it's going to be decreasing. At the 20, let's just say f 30, be a positive and a positive, so that would be greater than 0, so f prime there would make this an increasing function, which is what a cubic looks like. You know, a cubic's going to look something like this, and these dips and valleys occur at whatever points. I can look at this and know that I'm going to have a maximum here at negative 20 and a minimum here at positive 20. Let's see if it changes concavity. I believe that it will. So I'm going to test here at 0, and I've got to test double prime of, let's say, negative 1. This is a negative if I plug it in there, so it's less than 0, so that means this is concave down. That's what I expected. Over here on this side, f double prime of 1 is going to be greater than 0 when I plug that in. Yeah, that's exactly what I expected. So x equals 0 is point of inflection, because that is where it changes from concave down to concave up. Now, what's up on my list of intervals of increasing and decreasing? Let's write that out. That was number 5, increasing from negative infinity all the way up to negative 20, and from 20 all the way to infinity. Then decreasing from negative 20 to 20. Ooh. Okay. To 20. Alright, next on my list, horizontal and vertical isotopes. No vertical isotopes, I didn't have any problem with domain here. Horizontal isotopes, this thing doesn't have one, it's all top heavy, so no vertical isotopes, no horizontal isotopes. This thing is shooting up to positive and negative infinity. The intercepts, no, I'm on 7. Oh, that was number 7, sorry. What was number 6? Oh, extreme values. Okay, I got to do those extreme values. I see that x equal negative 20 is that was a maximum. X equal positive 20 is going to be my min, so this is a max and this is a min. Let me go ahead and get those points. I'm just going to plug into my original. I'm going to plug in a negative 20 and I'm going to plug in a positive 20 to my calculator. Alright, I got those numbers plugged in. I'll write those down. Need some more room here. That is going to be 5,333.3, and this is my max. No wonder I couldn't see it on my graph. And at 20, due to symmetry, it's going to be this. I expected that to be the case. This is my min. Then let's see, intercepts, where does it cross the x-axis? So for 8, I need to say, you know, at which point is it that 0 equals, or y is 0 here, so that would be, I think it was x cubed over 3 minus 400x. Move all that stuff over to either side, and well, first I'm going to factor, and then I would get x squared over 3 minus 400. X equals 0 is going to be 1, and then you'll need to move the 400 over, multiply by 3, and then take the square root, and you'll get the other 2 points would then be at, let's see, let me calculate the square root of, that'd be 1200 plus minus square root of 1200, whatever that is. If I crunch that on my calculator, I end up with plus minus 34.6. Alright, so let's think about what we've got here and what our viewing window needs to be. my y's need to go up to at least 5,000, so y's need to be, y needs to be in between, let's just say, how about 5,500, 6,000, somewhere around in there. We'll make it 6,000. I will put my y scale, I'll probably have it at 1,000, that way it doesn't have so many tick marks like this thing did. My x needs to go at least to the 20. Let's make it a pretty number. Let's just say -30 x 30, and my x scale, let's let that be, I don't know, let's have it count by tens. Alright, and then I'm going to graph that. Oh man, I forgot about those x-intercepts right there. This needs to go further than the 30, so I'm going to pull that out to 50. I'm going to see what that looks like. Oh, now this is nice. Okay, so these are counting by tens: 10, 20, 30, 40, and 50. Notice it crossing there at about 35 or so. Nice. There's my x, where it crossed the x-intercept there at 0, and then there is the symmetric part over there on the other side. These are counting by thousands, so there's 1,000, 2,000, 3,000, 4,000, 5,000. I can note that it is going a little above the 5,000. All that looks beautiful, and I know through calculus that I have all the important information. I know that it's not going to do anything else wacky. It's just going to keep on going up and up from here, because I found the places where it has significant change. Step 1. Let's look at the denominator. X can be anything where x is not equal to positive, -1. Can't have that. Now, the symmetry of this is elusive. You could go look up rules and determine that since this is an odd function divided by an even function, that you're going to get an odd function, and therefore it's symmetric about the origin. That's not entirely necessary that you go look up those rules, but you can. So we'll just go ahead and write down that this is an odd function, but that part not quite as definite that I have to know that. Because if I find all of these other points, then I tend to look at the function when it's graphed, have all the points on there, and go, oh yeah, look, it's symmetric about the, and I kind of note it on the back end instead of the front end if you really want to know how I do it. I'm going to find the first and second derivatives. Is going to be a little messy and tedious, so I'll do that. Wow, this was really messy. While I was doing all of this, I went ahead and got you a picture of that rational function with a standard viewing window of the -20 to 20 and so forth. Step number 4, find the possible critical points and points of inflection. I went ahead and factored it so that I could just look at it and say 0, plus and minus square root of 3, and plus and minus 1. Here would be x equals 0 and plus and minus 1, and I'll go ahead and write those down. Next thing I'm going to do is write out my number line, and then I'm going to have to test in between all of these points, which will be a very tedious, because I've got to test in between. There's 5 points here, so I've got to test on either side, and there are 3 points here, and I'll test on there. So I'm going to scroll down and make those lists. Alright, I've written my number line and points on either side and plugged things in. So at -2 over here, I know that my function is increasing because the first derivative is greater than 0. Then it's decreasing. Here it is decreasing from 0 to 1. That's my 0.5 point. That's also decreasing. At 1 and this 1.5, it's still decreasing. Strange. And now I am increasing again. Here at -2, less than 0, that would be concave down. This would be concave up, concave down, and then concave up. Interesting, very interesting. Now I know that I do have vertical isotopes here at positive and -1. Oh yeah, so if I look at this guy, notice how I don't really see what's going on here at the -√3 because I have vertical isotopes at 1 and -1, so I'm not seeing anything that's going on over in this realm. So I know that I'll have to change my viewing window in order to get what's going on here. Let's try and see if we can kind of get a handle on what's going on. I know that I had these vertical isotopes here at 1 and -1. It's that domain restriction that I just looked at. So in between here, I know that it's going down and it's going down. I also know that it changes from concave up to concave down. So I know it does some sort of thing that looks like concave up to concave down. So I know that's going on. But what's going on over in this realm? I don't have another vertical isotope, and I have just gotten this part done. So this tells me that it's going to go up and then down, and this tells me that that's what it's going to look like over in there because it doesn't change concavity. So it's got to be some sort of, over in here I can see that it doesn't cross, so it's either going to be something, well, since it doesn't cross, it can't really be up here, it's got to be down in here. And I can see that it's not crossing at that √3, which is 1.7 or so. And it looks the same thing over in here, so it's got to be some sort of something of like this. It's not crossing. I need to figure out what these points are here, so I think that's next on my list, to find the extreme values so that I can get what they are and get this in my viewing window and get my X and Y intercepts. So I'm getting ready to go get this point here. Let's get these extreme values. I know that at that f of √3, I'm going to have one. That one is going to be a minimum. And this f of -√3, I'm going to plug that into my original. I went ahead and snipped it so that you would get that. And I need to see that f of 0 as well. I didn't state inflection points. 0 is my inflection point. These places here are not going to be inflection points because they're not in the domain, but x = 0 is an inflection point. So I'm going to calculate those values. So I have my extrema. In looking at this one, looking at the limit as x goes to infinity, getting my horizontal isotopes. This one's top heavy, so I'm going to say limit of f of x. This thing is going to be shooting up to infinity, and limit as x goes to -infinity of f of x is going to be -infinity when I plug in that negative. The intercepts, I set this thing equal to, and when there's the vertical isotopes, we discussed it, 1 and -1. So I'll write vertical isotopes at x = positive -1. I'm finding the intercepts next. 0 = 10x³ over x² - 1. Basically you set the numerator equal to 0, because if the denominator is 0 it fails to exist, so that's not going to be an intercept. So x = 0, plug it back in the 0 to see what you get for y, and y = 0 is that is my intercept. And anything else? Nope, we're going to graph this thing. I think I'm going to use, let's look at my window and then I'll slap it down on this. For the y values, they need to go up to 15 times that. Square root of 3 is 1.7, so it has to be at least up to 30. So let's just go ahead and do the y's are going to be negative 40, y to 40, and y scale I'm going to count by tens. The x's don't really need to go too far. I'll just go from 5 to negative 5, and I'll count by ones, and I'm going to plop that graph down. Oh man, just when I thought I was done, I didn't even notice that the degree in the numerator was 1 over the degree in the denominator, which means I have a slant isotope, and I'm going to have to go find that dumb thing. Alright, give me a minute and I'm going to go do my division. Alright, that's as far as that one goes. There's my slant isotope. So I could say that f of x equals 10x plus 10x over x squared minus 1, and this is the equation for my slant isotope. So slant y equals 10x. Okay, now I think I have everything about this function from here on. Alright, all of the list is accounted for. These problems are long and tedious. I'll do the last two in another video.